Welcome to our Quantum Deep Dive. Today we're embarking on a truly captivating journey. We're going into the world of quantum information technology.
Right, a realm that often sounds like pure science fiction.
Exactly, but it forms the very bedrock of our digital future. And our focus today is on a visionary, someone whose work has fundamentally reshaped how we think about information, about security. Gilles Brassard. We'll be drawing our insights from a really comprehensive and insightful essay by Yorgo Schneeppot. It chronicles Brassard's incredible career and his profound impact.
And what's truly remarkable, I think, about Brassard's work is how his vision, which is rooted in, abstract physics, has consistently translated into tangible security solutions. We're talking about the promise of genuinely unhackable communication.
Unhackable, that's the key word.
It really is. It's a prime example of these, theoretical breakthroughs moving directly into critical real-world applications.
So, for you, our listener, what does this deep dive mean? Well, it means pulling back the curtain on the fundamental architecture of future cybersecurity and recognizing the sort of quiet giants who are building it right now.
That's a good way to put it.
Let's unpack this fascinating story and see how one person's deep fascination with math and physics blossomed into a revolution in data security.
Sounds great.
To really understand this revolution, maybe let's start by painting a picture of the man himself, who is Gilles Brassard. What set him on this extraordinary path?
Well, Gilles Brassard, born in Montreal, Canada in 1955, he grew up in an environment that really nurtured his intellectual curiosity.
Okay.
He showed exceptional talent for abstract thinking from a very young age. And this wasn't just about being smart, academically bright.
Right.
It was more a profound, deep-seated drive, a need to understand the underlying principles of computation and information itself.
And that drive, that early curiosity, that led him to some pretty foundational interests, didn't it? Things that would define his career.
Absolutely. His early fascination with mathematics and computer science was, profound, even before these fields really gained widespread academic attention.
Interesting.
He wasn't just dabbling, he was deeply delving into algorithmic concepts, the intricacies of cryptography.
Right.
And he was particularly influenced by the classical works, people like Alan Turing,
Of course.
who laid the groundwork for computation, and Claude Shannon, the father of information theory.
Right, Shannon.
These early influences really sparked his interest in that exciting intersection of computer science, math, and crucially, the fundamental principles of physics.
It sounds like a truly fertile intellectual environment. But to really shape the future, a mind like Brassard's often needs bigger challenges, right? So where did his journey take him from Montreal? How did that new environment crystallize his ideas?
Well, his potential quickly earned him a move from the University of Montreal to the world-renowned Massachusetts Institute of Technology, MIT.
MIT.
Yeah.
Makes sense.
And this period was absolutely crucial. It was at MIT that he began to intensively explore this groundbreaking question. How could quantum effects? There's, bizarre, counterintuitive phenomena of the subatomic world. How could they revolutionize information security and computational power?
So that's where it all started to come together.
Exactly. It's where those early fascinations started to crystallize into, truly groundbreaking research that would change everything.
Which brings us neatly to 1984, a pivotal year. Brassard, working alongside Charles Bennett, created something revolutionary. The BB84 protocol. What made this protocol such an absolute game changer for cryptography?
Well, BB84 was monumental because it fundamentally shifted how we secure information. Before BB84, classical cryptography, like RSA,
Right, the standard stuff?
it relied on mathematical assumptions, basically how hard it is to factor huge numbers.
Okay.
But BB84 introduced a method leveraging the inherent security of quantum mechanics itself.
Inherent security.
Yes. It used fundamental quantum principles, like Heisenberg's uncertainty principle and quantum entanglement, to guarantee its security, not just make it hard.
Okay, let's unpack that. Inherent security, Heisenberg's uncertainty. What does that actually mean for how BB84 works? Give us the aha moment.
Okay, so at its core, BB84 lets two parties, usually called Alice and Bob,
Alice and Bob, always.
always Alice and Bob, they securely exchange a secret key. And they do this by sending quantum bits, qubits, often encoded as single particles of light photons.
Photons, okay.
Here's the clever part. Alice encodes these photons in one of two randomly chosen bases. Think of it like orienting a photon in one of two ways.
Okay.
That an eavesdropper wouldn't know how to measure without messing it up. She sends these coded photons to Bob.
Right.
Bob then randomly measures the photons he receives using one of his two bases, and here's the magic. If he chooses the wrong basis, the very act of measuring alters the original quantum signal. It disturbs it.
So it's not just making it difficult to eavesdrop. It's physically impossible to do so without being noticed.
Exactly that. After Bob measures, Alice and Bob publicly compare which bases they used. Importantly, not the values they measured.
Just the settings, okay.
Just the settings. They only keep the measurements where their bases matched, and from those matching measurements, they generate a shared secret key.
And the eavesdropper, Eve.
Right, Eve. If she tried to intercept and read those photons, her attempt to measure them would, by the laws of quantum mechanics, inevitably disturb their fragile state.
Because you can't measure without affecting it.
Precisely. So when Alice and Bob compare notes later, those disturbances show up as errors or inconsistencies. It immediately signals Eve's presence.
And that relies on the no cloning theorem, right?
Exactly. A fundamental rule. You cannot perfectly copy an unknown quantum state. Trying to copy it inevitably changes it. It's like trying to photocopy a quantum state ruins the original.
That's an incredibly powerful idea. But, moving from theory to practice in quantum, that's often the huge hurdle.
It is.
Were Brassard and Bennett able to actually prove this works in the real world?
They were indeed. In the early 1990s, Brassard and his colleagues, John Smolin was key here too, conducted the first pioneering experiments.
Okay.
They actually transmitted quantum keys over optical fibers. They proved encrypted data could be successfully sent using photons.
And the eavesdropping detection.
Crucially, yes. Their experiments confirmed that any attempt at eavesdropping caused measurable changes, proving the protocol's feasibility. This was despite, initial technical challenges like photon loss in the fiber.
Wow.
But it really cemented BB-84's practical relevance, showed the world quantum crypto is more than just a theoretical dream.
That partnership with Charles Bennett, it seems foundational. Beyond BB-84, where else did their combined genius lead them? What other big ideas came out of that?
Oh, their collaboration was exceptionally fruitful, really pushed the boundaries. Beyond BB-84, they published the first theoretical description of quantum teleportation in 1993.
Quantum teleportation. Okay, that sounds like pure sci-fi.
It does, but it's not about physically moving an object like in Star Trek.
Right, beaming Scotty up.
Not quite. It's about transferring the state of a qubit, its quantum information from one location to another, without the physical qubit itself traveling that distance.
How on earth does that work? What's the secret?
Well, it hinges on three key quantum principles. First, quantum entanglement.
Entanglement, okay. The spooky action.
That's the one. Two qubits become intrinsically linked, sharing a state regardless of distance. Second, a specific measurement is performed on the qubit you want to teleport, and on one of the entangled pair.
Okay.
This measurement actually destroys the original state, but gives you classical information about it. Third, this classical communication, the measurement results, is sent just normally to the receiver.
So you send classical info.
Yes. And the receiver uses that information to perform an operation on their entangled qubit, perfectly reconstructing the original quantum state.
So it's like sending the blueprint, not the object itself.
That's a great analogy. Exactly. Sending the instructions to rebuild it perfectly.
That's absolutely mind-blowing. And they didn't stop there, right? With key exchange or teleportation.
Yeah.
They kept pushing quantum communication forward.
No, they kept innovating. Absolutely. They explored various quantum key exchange methods, always emphasizing entanglement's role, and how even quantum noise, usually seen as a problem, could actually be harnessed as a security feature.
Interesting twist.
Right. This whole intellectual ferment led to other key protocols, like E91 from Archer Eckert, which built on their ideas using entanglement directly for keys. Their work moved quantum crypto from, a theory curiosity to a field really on the verge of practical use.
It really highlights that blend of fields. For our listener, what does this interdisciplinary approach, marrying computer science, math, physics, tell us about breakthrough innovation?
Stepping back, their work perfectly exemplifies how abstract theories from physics, superposition, entanglement, no cloning are formalized using rigorous mathematics to create secure algorithms and then implemented through computer science to build actual real-world systems.
So it's connecting the dots.
Exactly. They built this robust intellectual bridge between these seemingly separate fields, and that paved the way for a whole new generation of researchers and engineers. It showed the biggest problems often need that cross-disciplinary thinking.
So given all these incredible contributions, how has Brassard's work actually impacted academia and industry? What's the legacy?
The impact is fundamental, really far-reaching. Academically, his research deepened our understanding of quantum mechanics and its applications immensely. He opened up whole new lines of inquiry, inspiring ongoing research in quantum key distribution, QKD, new quantum algorithms, even fundamental quantum mechanics itself.
And industrially?
Industrially, his core concepts are now the foundation for numerous commercial quantum cryptography systems being developed and deployed as we speak.
Can you give us some concrete examples? Where are we seeing Brassard's ideas at work now?
Sure. Companies like ID Quantique, Toshiba, Quantum CTech. They've developed cutting-edge products directly based on his foundational ideas. These systems are being deployed in highly sensitive areas: finance, healthcare, national security, securing critical data.
So, real-world applications.
Absolutely.
Yeah.
Quantum-secured links between banks, government agencies, even quantum satellite communication. China's Mischief satellite is a prime example, used for secure, long-distance key exchange. It proves the global reach and viability.
Beyond the research itself, it sounds like he was also a significant mentor, a community builder.
Yes, definitely. His impact goes way beyond the papers. He played a crucial role in fostering young scientists, establishing entirely new research fields. As a professor at the University of Montreal, he mentored countless researchers who are now leaders in quantum information science globally. He helped create and define fields like quantum information theory, quantum security architectures, and even the vision of a future quantum internet.
Shaping the field and the people in it.
Exactly. Shaping the technology and the minds who would build it.
And all this groundbreaking work, mentorship, field building, it didn't go unnoticed, I assume. What recognition has he received?
Oh, absolutely not unnoticed. His scientific excellence is acknowledged with numerous, very prestigious awards. Most notably, perhaps, the Wolf Prize for Physics in 2018.
The Wolf Prize? Wow.
Yeah, a huge honor. He shared it with Charles Bennett, recognizing their pioneering work in quantum information, especially quantum crypto and teleportation.
That makes sense.
He also got Canada's Killam Prize, holds a Canada Research Chair, many other significant honors. These really underscore the profound global impact of his contributions.
It's clear Brassard was focused on security, but his vision also extended to making computers smarter, faster, right? Through quantum algorithms. What did he contribute there?
He did make significant contributions there too, yeah. Understanding how quantum computers could solve problems much more efficiently than classical ones. A central theme was optimizing search. He collaborated on the theoretical foundations for Grover's algorithm.
Grover's algorithm. The search one.
That's the one. It can search unstructured databases dramatically faster than any classical method.
How much faster are we talking? Can you give us a sense of that speed up?
Well, classically, searching a list of n items takes roughly n steps. Grover's algorithm reduces this to O, square root of n.
Square root, okay.
So, for a list of 1,000,000 items, a classical computer might need, worst case, 1,000,000 steps. A quantum computer using Grover's could potentially do it in about 1,000 steps.
1,000 versus 1,000,000, that's huge.
It's enormous. Imagine that applied to vast drug discovery databases or complex optimization in finance or logistics. It's a potential game changer for finding needles in digital haystacks.
And he saw potential beyond just search, right? In AI, maybe.
Absolutely. He recognized the potential in areas like optimization and artificial intelligence. Quantum computers don't just offer speed. They open new possibilities for machine learning, data processing.
Like what?
Things like quantum enhancements for neural networks, quantum-based pattern recognition. It's about opening up entirely new computational approaches.
He also collaborated with other giants, like David Deutsch. How did that synergy work?
Yeah, their collaboration was really potent. Deutsch provided the fundamental theoretical framework for the universal quantum computer, what it could be.
The big idea.
The big idea. Brassard helps substantiate that vision with specific algorithms and protocols, showing its practical capabilities, its applicability. It was that perfect blend of fundamental theory and applied innovation.
So despite all these breakthroughs, the vision.
Yeah.
What are the major challenges still facing quantum information tech? What are the roadblocks?
Oh, the challenges are still significant, both technical and theoretical. Technically, just scaling up quantum computers to be large and fault-tolerant is incredibly hard.
Right, stability.
Exactly. Battling decoherence where quantum states just fall apart. Developing robust quantum error correction is a massive ongoing effort.
And for QKD, the key distribution.
Limits to range in optical fibers is a big one. You lose photons. So you need things like quantum repeaters, which are complex. And then just integrating these new quantum systems with our existing classical networks. That's a huge hurdle.
And theoretically,
proving the security of new protocols in noisy real-world conditions is tough. And we're always searching for more killer quantum algorithms for problems in medicine, climate change, materials, beyond Shor's and Grover's.
So despite these challenges, what was Brassard's ultimate vision? What was he aiming for with all this?
His vision was remarkably consistent. An absolutely secure communication infrastructure based purely on quantum mechanics, immune to all attacks, even from future quantum computers.
A truly secure internet.
A global quantum internet, yeah. Using satellites, terrestrial networks for seamless, physically unhackable communication. But he also stressed the ethical side.
Important.
Very. The responsibility that comes with such powerful tech, advocating for international oversight to prevent misuse.
And finally, as we rack up, what future developments are still being driven by his foundational work today?
Yeah.
Where are the ripples still spreading?
His work continues to drive innovation everywhere. We see progress towards global quantum satellite networks for secure comms across continents. Lots of work on hybrid quantum classical systems, blending the old and new tech. Advances in quantum error correction are critical and ongoing.
Okay.
And beyond that, new protocols for secure multi-party computation, think blockchain, secure cloud computing, specialized quantum accelerators for science, for machine learning. His ideas are still powering the field forward.
Gilles Brassard really stands out, doesn't he? One of the undisputed founding figures of quantum information technology.
Absolutely.
His relentless curiosity, his groundbreaking work, BB-84, quantum teleportation, quantum algorithms. He shifted quantum mechanics from abstract theory into a powerful tool for real-world problems.
And his vision for secure quantum communication, it continues to inspire everything from quantum satellites to the commercial crypto systems running today. He didn't just innovate, he fostered a global research field, mentored countless scientists, proving that knowledge is most valuable when understood and applied.
That interdisciplinary approach to marrying physics, math, computer science, it deepened our understanding and opened totally new avenues. The Wolf Prize, all those honors. That really testament to the huge significance of his work worldwide.
Which leaves us with a fascinating question, doesn't it? As we actually build this global quantum internet, develop more powerful quantum computers, how will society adapt to this, well, unparalleled level of information security?
A future he envisioned and helped lay the groundwork for.
Precisely.
We really hope this deep dive into the extraordinary work of Gilles Brassard, informed by Jurgo Schneppat's excellent essay, has given you some profound new insights. Thank you for joining us for this exploration.
And for more information on this and related topics, you can visit schneppat.de.
Goodbye for now and keep exploring.